Okay, so in this video we're going to finish off our topic of radioactivity. We're just going to look at two things. We're going to look at the radius of a nucleus, how it depends on the mass number, and then we're going to look at the density of the nucleus and to see if we can prove whether or not the density is always the same or if it varies depending on the size of the nucleus. So first up, let's just do some very simple modelling in order to get, what we're trying to get is to the equation that you're given on the AQA formula sheet, that R, the radius of the nucleus, is equal to RO, we'll come to what RO is in a second, A to the power of a third. So let's just look at this from the ground up. What would the volume be of one proton or neutron, so a nucleon, with radius RO? So you can see what the RO is down here. So here we've got very simple idea. This is a nucleon. What would its volume be? Straightforward. The volume of the nucleon would be 4/3 pi r cubed, where R is RO. Let's now think of a nucleus, and inside this nucleus there are A nucleons, and the nucleus has got a radius of big R. So imagine I've tried to show all of the nucleons are inside the nucleus. So what would its approximate volume be? Well, its volume is going to be 4/3 pi R, big R cubed, which is the radius of the nucleus, and this is going to be equal to approximately to A, which is the number of nucleons, multiplied by V little n, which is the volume of one nucleon. Because assuming there's not much space between them all, the volume of all the nucleons, if you added all that up or multiplied it by the number that there are, you're going to get an answer that's fairly similar to this expression here, which is 4/3 pi big R cubed. So what could we do with these two equations? In physics, if we've got two equations, we want to try and combine them. So my hint is replace Vn in the second formula, replace this Vn with this expression, and then we can do some cancelling and rearranging. So here we go. 4/3 pi r cubed is equal to A, and this expression here is V little n, the volume of a nucleon, 4/3 pi RO cubed. So straight away you can see certain things cancel. We've got rid of the 4/3, haven't we? So we end up with we've got rid of the 4/3 pi, sorry, so we end up with big R cubed is equal to A RO cubed, and with a little bit of messing around we can soon get to the formula that you're given on the data sheet. So this formula states that the radius of a nucleus is equal to the radius of a nucleon multiplied by the mass number to the cubed root, to the third root, sorry. Alright, so that's what this formula means, and in terms of how we get it, you can see with this little model here we've got to it quite straightforward. So what we're suggesting here is that the mass of the nucleus depends on A, the number of nucleons in the nucleus. The radius of a nucleus is approximately, remember the assumption in the derivation, the assumption being that all of the nucleons together, all of the volume of the nucleons together is pretty much equal to the volume of the nucleus. And so the radius of the nuclei is linked to the mass number A by the following equation. And note that this is a constant. You won't find it on the data sheet, but we are saying that RO is a constant, and it's effectively the radius of a single proton or neutron, a nucleon, but this can vary sometimes dependent on the question. All right, so, and remember that this is only a model. If you think right back into year 12 physics, the proton neutron is really made of three dense points, and those three dense points being quarks. Alright, so let's try and find the value of Ri by plotting some graphs, and we're going to plot three potential graphs. When you're watching this video, in some respects I'm going to go through it really quickly. It may be worth you attempting to go and plot these graphs yourself. I'm just going to show you the graphs after I've used Excel to plot them. So the first graph we're going to do is a straightforward graph. We're going to plot the radius against the nucleon number and look at the general shape. Then we're going to plot the radius against A to the power of a third, and then we're going to plot some log graphs, all right, and the hints coming up in a second. And remember, what we're after here is that the RO, the radius of a nucleon, we're probably going to be in the region of 10 to the minus 15, which is femtometers. So first graph that you need to know the shape of, this is graph 1. If we quite simply plot the radius of a nucleus against the nucleon number, here's the data I've used. If you did want to go and pause this and go and shove this into an Excel document and do it yourself, I've just got a few isotopes here and their radius, known radius from using electron diffraction, and their mass number. All right, so this first graph, radius of nucleus, that column here, against nucleon number, this column here, and we get unsurprisingly, I suppose, that initially the radius of the nucleus increases significantly and then it levels off. The reason it's levelling off is if you imagine the model of like adding lots of little balls to make up a big ball, or adding lots of nucleons to make a nucleus, then initially when you start to add a nucleon in, a proton or a neutron in, the radius increases significantly, and then as you get to more and more nucleons, the increase is not really significant. If you imagine if you had 50 golf balls and you added another golf ball inside a football, you could quite easily get another one in, and the size of the football that you needed wouldn't increase that much. So you've got to know this general shape, okay? And the general shape is it starts off very steeply and then flattens off. So that's the first graph. The second graph we suggested was let's plot radius of nucleus against a to the power of a third to find r. Looking at our formula, y equals mx. This should be a straight line with r on the y-axis, radius of the nucleus, on the x-axis, a to the cube, a to the power of a third. All right, so if you put these into Excel and put them to the power of a third, you're going to get this relationship, which is a pretty straight line. You can see my data there, and my gradient here is coming out to be 1.225, and remember I'm still in femtometers, so this is going to be 1.225 times 10 to the minus 15. So that's one way of finding the constant, is by plotting the radius against a to the power of a third, and it comes out to around 1.1, 1.2. Dependent on what data and what straight line you end up drawing through your points. Okay, and the final one would be to do some natural logs, some ln's. So let's just see how I've done this. I've plotted ln r against ln a. Look at our initial formula, r equals r0a to the third. Let's take logs of both sides, straightforward. And then what we can say is, let's split this out using the log rule, log r0 plus log a to the third. Then we can move this third down here, can't we, to give us third natural log a. So I've just done that, a third natural log a. And this is starting to look like a y equals mx plus c. If I just move it round, I've just moved the plus third log a over here. So now I've got y equals mx plus c. So if we plot log r there against log a there, our gradient should be a third, and our intercept should be the natural log of r0, the radius of a nucleon. Here's my Excel graph. Y equals 0.3421, so that's not far off a third, is it? Plus 0.1838. So if I just put e to the power of 0.1838, I'll get 1.2, which again, we're still in femtometers, that's 1.2 femtometers. So again, you can see the constant r0 is coming around the 1.1, 1.2 for whichever method we've used. So the last two methods are probably more important to be able to do. The first graph you need to know the shape of, just in case you get asked to plot it. Okay, then to finish up, let's just talk a little bit about density. If we assume the nucleus is spherical, let's just see we've got here the volume will be 4/3 pi r cubed. This is big R, the nucleus. So 4/3 pi, let's just insert for big R our expression, the radius of a nucleon, a to the power of a third. So radius of a nucleon, a to the power of a third, and all that's been cubed. Now just cube, let's just apply this cube here. So r0 cubed, a to the third cubed is just a. So we've got an expression here for the volume of a nucleus, which is 4/3 pi r0 cubed multiplied by a. Worth remembering how to do that. Let's bring in our density equation now. So density is mass divided by volume. So mass divided by 4/3 pi r0 cubed a. Let's express our mass not in terms of m, but let's express it in terms of a times the mass of a nucleon, a being the mass number. And now what we can do, you can see here, we can start to cancel in a's and sort stuff out. So a times mass of a nucleon divided by our expression for volume. Let's just see what we can do with that. I'll flip my 3/4 and put 3 on the top, 4 on the bottom. So I've just done that in one step, and then hopefully you can see how my a's cancel to give me 3 mass of a nucleon divided by 4 pi r0 cubed. And if we wanted to put some numbers in this, we could now calculate the density. Notice here, 3 is a constant, mass of a nucleon is pretty much constant, 4 constant, pi constant, and RO is a constant. We've set it to about 1.2 femtometers. So all of these are constants. So that's what we're saying here, what we're suggesting is that the nuclear density is a constant. So let's just put some numbers in and work out what it is. If you put the numbers in 3, mass of a nucleon, 1.67 times 10 to the minus 27, 4 pi, I've used 1.05. Again, it just depends what you end up given or what you use, as long as it's in the region of 1 to 1.2 femtometers. I've put it in and cubed it, and I'm getting a density of, wow, 3.4 times 10 to the 17 kilograms per meters cubed. I think if you do some maths on this, that's about, I don't know, it's about a teaspoonful, or let's not even say a teaspoonful. If you worked out a cubic millimeter of nuclear material, so imagine a cube with sides of a millimeter, the mass of that is a couple of battleships, I think, or a couple of aircraft carriers. So this is a phenomenal density, and if you've studied the astrophysics module, you can start to appreciate this is in the region of neutron star density, etc. All right. So other conclusions from the formula: density is a constant in any nucleus. It's independent of its radius r. Notice in this formula there isn't any r, any big R. So density is constant for all nuclei, which means that the nucleons always must be separated by the same distance, whether it's a big nucleus or a small nucleus, so they don't get squashed. This is the general idea, that the nucleons do not get squashed. And remember, this is a model. The whole thing is based on our model of the nucleus. The whole thing is made of quarks, when we really start to think about what stuff is actually made of. And a couple of calculations to finish. I'll just show these really quickly so you can pause it and check them yourself. Calculate the radius and volume of a uranium-238 nucleus. Take RO to be 1.05 femtometers. This is straight use of the equation that you're given, so this will be a very easy exam question. I've got an answer of about 1.2 times 10 to the minus 42 meters cubed. And then so the volume would be there, yeah. Then come down here, let's go, the volume of silicon-28 nucleus is 1.4 times 10 to the minus 43 meters cubed. Use this to calculate the radius of the nucleus, then RO, and finally use your data to calculate the radius of a tin 120. So first of all, let's just use V equals 4/3 pi r cubed. Rearranged it, check your maths, R equals the cube root of 3V over 4 pi. So put some numbers in, I get 3.2 femtometers. So this is the radius of the nucleus. Then I'm going to put this into our formula up here to calculate a value of RO. So RO equals R over A to the third, 3.2 times 10 to the minus 15, our previous answer, divided by 28 to the third, because I told you here silicon was. This gives us a value of R to be 1.03 times 10 to the 5 minus 15 meters. And then the final question is finally the radius of a tin 120 nucleus. So again, using this formula, now let's put in our value that we found for RO and go RO multiplied by A to the third. For tin it's 120, so 120 to the power of a third, and we get a value of big R, the radius of a tin 120 nucleus, to be 5.2 femtometers. So hopefully you can see how in questions you're going to be asked to either find RO, even though it's a constant, but find a value for it, or you're going to be asked to use it to calculate the radius of another nucleus.